Hi, in this presentation we'll explore how to find the modular square root with a prime modulus, a fundamental concept in number theory that also plays a crucial role in fields like cryptography, computer science, and algorithm design. Section 1 kicks off with a demonstration of how to apply Niven's congruence to primes of the form 4k plus 3 and 8k plus 5. In Section 2, we will develop an infinite descent method tailored for primes of the form 8k plus 1. Finally, in Section 3, we'll take a fresh look at the Tonelli-Shanks algorithm, not from the usual computational angle, but by breaking down its mathematical components to uncover a simplified congruence we'll refer to as the Tonelli-Shanks formula. In his book, An Introduction to the Theory of Numbers, Ivan Niven explores the topics of quadratic congruences with a prime modulus. He begins by referencing Euler's criterion, which states that if n raised to p minus 1 over 2 is congruent to 1 modulo p, then the modular square root m for a prime p of the form 4k plus 3 can be computed as the residue m of n raised to p plus 1 over 4 modulus p. This result follows since the square of n raised to p plus 1 over 4 equals n raised to p plus 1 over 2, which equals n times n raised to p minus 1 over 2, which is congruent to 1 modulo p given Euler's criterion. In other words, the solution to the quadratic congruence is obtained in just a few straightforward steps. To find the modular square root of n modulus a prime p of the form 4k plus 3, we begin by verifying Euler's criterion for n. Next, we multiply both sides of the congruence by n and substitute p as 4k plus 3, simplifying the exponent, which yields 2 times k plus 1, which can be expressed as the square of n raised to k plus 1. Finally, we compute the residue m of n raised to k plus 1 modulus p, leading to the solution. M squared is congruent to n modulus p. Here, you can visualize a couple of examples using the prime 79. For the residue 11, we follow the procedure outlined earlier step by step. However, for the residue 17, we streamline the process. Since 79 is a prime of the form 4k plus 3, the only essential steps are verifying Euler's criterion and computing the residue of n raised to k plus 1 modulo 79. Continuing with the same prime 79, we compute the modular square roots for the initial values. In addition to primes of the form 4k plus 3, we have those of the form 4k plus 1, which can be further categorized into 8k plus 1 and 8k plus 5. Fortunately, Niven's congruence also applies to primes of the form 8k plus 5, as we will demonstrate shortly. However, primes of the form 8k plus 1 require special treatment. While Niven employs Tonelli-Shanks algorithm for these cases, we will instead introduce an infinite descent method in Section 2. When working with primes of the form 8k plus 5, the procedure is largely similar to the case of 4k plus 3. However, since 4 divides p minus 1, it introduces two distinct cases. If the residue is 1, the solution is straightforward and follows the same steps as before, with adjustment of substituting p as 8k plus 5. If the residue is minus 1, following the same steps as the previous case leads to a partial solution. M squared is congruent to minus 1 modulo p. To resolve this, we introduce a quadratic non-residue u. Combining this congruence with a partial solution obtained before, we rearrange the left-hand side into a perfect square, leveraging the fact that 4 divides p minus 1. Finally, to determine the solution m squared congruent to n modulo p, we compute the residue of m times u raised to p minus 1 over 4 modulo p, achieving the desired result with n as the residue. Since p plus 3 over 4 equals 2 times k plus 1, we can deduce the following formula for case 2. The square of n raised to p plus 3 over 8 times u raised to p minus 1 over 4 is congruent to n modulo p. Let's walk through an example with a prime 109. We'll explore two cases. In case 1, p divides n raised to p minus 1 over 4 minus 1. So finding the modular square root of m squared congruent to 5 modulo 109 is straightforward, following the same procedure detailed before. 21 squared is congruent to 5 modulo 109. In case 2, p divides n raised to p minus 1 over 4 plus 1. Following the same steps lead us to a partial solution. 25 squared plus 29 is divisible by 109. To move forward, we need to find a quadratic non-residue of 109. Testing more integers, we find that 2 works as a quadratic non-residue. Next, we combine this congruence with a partial solution, rearrange it so that the left-hand side becomes a perfect square, and compute the residue of 25 times 2 raised to 109 minus 1 over 4. The final result is 62 squared is congruent to 29 modulo 109. To find the modular square root for primes of the form 4k plus 1, Niven introduces the Tonelli-Shanks algorithm. In this section, we will instead present an infinite descent method as an alternative for primes of the form 8k plus 1, offering comparable efficiency. Then, in section 3, we will unpack the Tonelli-Shanks algorithm through a mathematical lens, and later compare it with the infinite descent method. The infinite descent method begins by considering a prime 8k plus 1. We express k as 2 raised to r times s, where r is equal or bigger than 0 and s is odd. Since s plus 1 is even, we write s plus 1 equals 2 raised to w times z, where w is equal or bigger than 1 and z is odd. First, we check that n is a quadratic residue of p, so p divides one of these two cases. Second, we multiply both sides of the congruence by n raised to 2 raised to r plus 1 and simplify. Third, we substitute p as a times 2 raised to r times s plus 1 into the exponent and then simplify. Fourth, we replace s plus 1 as 2 raised to w times z. After rearranging, we get that n raised to 2 raised to w minus 1 times z raised to 2 raised to r plus 2 is congruent to plus minus n raised to 2 raised to r plus 1 modulo p. Fifth, we determine the residue modulo p. If the sign is positive, something we already found in the first step above, we obtain our first difference of squares. If the sign is negative, a sum of squares. If the sign is positive, we can factor that difference of squares. So p must divide one of the two brackets. The process of infinite descent begins with testing for divisibility. If p divides the first factor, we deal with a second difference of squares, proceeding to factorize it further and continue testing divisibility, progressively working with smaller exponents until the desired solution is reached. On the other hand, if p divides a sum of squares, as in the second bracket, we must identify a quadratic non-residue u to proceed with the calculations. So we find a quadratic non-residue u and combine the congruences, so as to change the sign at the right side of the congruence, thus converting the sum of squares into a difference of squares. Next, we replace p as a times 2 raised to r times s plus 1, and rearrange the terms in the exponents to form a perfect square in the left-hand side. Finally, we compute the congruence, thus reaching a clear second difference of squares. This recursive process illustrates how infinite descent works, systematically reducing exponents and simplifying the congruence step by step. As you may have noticed, these congruences are essential for implementing the infinite descent method. Next, we'll delve into a detailed example, followed by a condensed version to showcase the method's efficiency. Now, let's compute the modular square root of 17 modulo prime 353. Using the previously outlined procedure, and as 353 divides 17 raised to 353 minus 1 over 4 minus 1, that leads us to the first difference of squares. Notice that since the values of n and s are already known, we can directly calculate w and z as well. With these values in hand, we can skip the intermediate steps and directly apply the congruence highlighted in green. Continuing, we factorize this first difference of squares and find that 353 divides a sum of squares. To move forward, we identify the smallest quadratic non-residue and combine the congruences, enabling us to change the sign on the right-hand side and form a perfect square on the left-hand side. After calculating the residue, we obtain a second difference of squares. Applying the same procedure, we derive a third difference of squares. Repeating the method one final time, we arrive at the solution. 82 squared is congruent to 17 modulo 353. Here, we present the previous deduction in a more streamlined form, emphasizing the concise representation of the descent. Notably, we can now take this a step further by condensing all steps into a single congruence. It is important to highlight that in this specific case, each factorization consistently revealed that 353 divides a sum of squares rather than a difference of squares. This recurring pattern leads to the elegant emergence of the sum of consecutive powers of 2. However, this neat structure does not necessarily apply to other residues or primes, where variations may occur. So we can condense all steps into a single infinite descent formula. In this formula, the exponent of the quadratic non-residue u, the sum of the powers of 2, features a sum of squares whose values must be smaller than r. This relates with the Tonelli-Shanks formula, to be introduced later, where the specific values must also be determined. Additionally, the infinite descent formula incorporates the function theta sub I, which takes the value 0 if p divides a difference of squares, or 1 if p divides a sum of squares. While this formula is not operationally more efficient, since deriving the difference of squares must still be done methodically, it serves as an elegant representation of how the method functions. It encapsulates the logic of the process in a unified expression, offering a clear conceptual framework for understanding the method's mechanics. Tonelli-Shanks algorithm can be challenging to grasp initially, as it requires some theoretical understanding. However, with a few examples, the computations becomes more straightforward. The algorithm leverages the property of the multiplicative order of n modulo p, that is, the smallest positive integer k such that n raised to k is congruent to 1 modulo p. When a and b that are co-prime to p and both having order 2 raised to j modulo p, given that a raised to 2 raised to j is congruent to 1 modulo p, then a raised to 2 raised to j minus 1 is not congruent to 1 modulo p, because 2 raised to j divides p minus 1. So a raised to 2 raised to j minus 1 is congruent to minus 1 modulo p. The same logic applies to b. So b raised to 2 raised to j minus 1 is congruent to minus 1 modulo p. Consequently, a times b raised to 2 raised to j minus 1 is congruent to 1 modulo p, indicating that a times b has order 2 raised to h modulo p, where h is smaller or equal to j minus 1. Given that p minus 1 equals m times 2 raised to k, where m is odd, for an integer x, we have x raised to m raised to 2 raised to k equals x raised to p minus 1, and that is congruent to 1 modulo p because of Fermat's Fiedel theorem. When x is a quadratic non-residue, then x raised to m raised to 2 raised to k minus 1 equals x raised to p minus 1 over 2, which is congruent to minus 1 modulo p. Thus, the order of x raised to m cannot be smaller than 2 raised to k. In fact, its order is 2 raised to k. When x is a quadratic residue, the order of x raised to m divides 2 raised to k. By repeatedly squaring x raised to m, we can accurately determine its exact order. The key point is that when x is a quadratic residue, x raised to m raised to 2 raised to k minus 1 is congruent to 1 modulo p, indicating that the order of the quadratic residue is smaller than the order of the quadratic non-residue. So by combining a quadratic residue and a quadratic non-residue within this framework, we can reach the solution in a finite numbers of iterations. Let's now unpack Tonelli-Shanks algorithm. This algorithm is typically introduced as a straightforward recipe, outlining a series of steps to reach the solution. However, what is missing is a clearer display of its mathematical building blocks. When trying to determine the modular square root, x squared congruent to n modulo p, where n is a quadratic residue and p minus 1 equals q times 2 raised to k, where q is odd, Tonelli-Shanks algorithm starts by setting the square of n raised to q plus 1 over 2 congruent to n times n raised to q modulo p, plus finding a quadratic non-residue z modulo p, whose order z raised to q is 2 raised to k. Next, find by checking values the order of 2 raised to k sub 1 of n raised to q. That is, the smallest k sub 1 bigger than 0 and smaller than k, such that n raised to q raised to 2 raised to k sub 1 is congruent to 1 modulo p. Once found, we apply z raised to q times 2 raised to k minus k sub 1 on both sides of a congruence. Next, proceed with squaring and determine by checking values the order of 2 raised to k sub 2 of n raised to q times z raised to q times 2 raised to k sub 1 minus k sub 2. That is, the smallest k sub 2 bigger than 0 and smaller than k sub 1, such that it raised to 2 raised to k sub 2 is congruent to 1 modulo p. Then apply z raised to q times 2 raised to k minus k sub 1, all of which raised to 2 raised to k sub 1 minus k sub 2 on both sides of a congruence. We'll need to repeat the procedure until the product of brackets at the right side are congruent to 1 modulo p, thus reaching the solution. This procedure might seem rather messy because the numbers get really big when the algorithm requires further iteration. You can always apply modulo p to the values and work with smaller numbers, which is the usual approach, by the way. But there's something to be learned by not applying congruences and instead linking up the powers. This approach enables us to discover a Tonelli-Shanks formula. Let's proceed step by step. First, consider a case that requires only one step to reach the solution. On the left side of the congruence, the exponent of c is q times 2 raised to k minus k sub 1 minus 1, which is equal to q times 2 raised to k minus 1 over k sub 1. Since q times 2 raised to k minus 1 equals p minus 1 over 2, we can simplify the expression. Therefore, the exponent of z is p minus 1 over 2 times 1 over 2 raised to k sub 1. The same reasoning applies to the right side of the congruence. Next, we apply the same procedure for a case that needs 2 steps to reach the solution. Note that the gray block simplifies into z raised to q times 2 raised to k minus k sub 2. This reveals that in step alpha, we are applying to the exponent of z the product of q times 2 raised to k minus k sub alpha. When combining this, the exponent includes the sum of the reciprocals of 2 raised to k sub 1 and 2 raised to k sub 2. When dealing with 3 steps, the solution involved the sum of the reciprocals of 2 raised to k sub 1, 2 raised to k sub 2, and 2 raised to k sub 3. Therefore, when m steps are needed, the exponent includes the sum of the reciprocals of the separate k sub m values. Remember that k sub 1 is smaller than k, that k sub 2 is smaller than k sub 1, and so on. Finally, as the brackets on the right side are congruent to 1 modulo p, the Tonelli-Shanks formula is revealed. We should clarify that this formula doesn't offer a significant advantage over the algorithm, as computing the k sub m values still involves dealing with the previous figures. However, this formula provides a clearer view on how these multiplicative orders 2 raised to k sub m play in the final result. Let's see an example. Let's find the modular square root of x squared congruent to 41 modulo 769. We check that 41 is indeed a quadratic residue of that prime, and by checking values, we find out that 7 is the smallest quadratic non-residue. Next, we apply the initial equation provided by Tonelli-Shanks algorithm. Note that it involves 41 and 3, the quadratic residue, and the odd quotient of 769 minus 1. Then, we know that 7 raised to 3 has order 2 raised to 8, as 7 is a quadratic non-residue, so 7 raised to 3 raised to 2 raised to 8 minus 1 equals 7 raised to 769 minus 1 over 2, which is congruent to minus 1 modulo 769. Next, we need to find the order 2 raised to h of 41 raised to 3. And here we need to check a short list of values as h is smaller than k. We find out that h equals 6, and so we can apply 7 raised to 3 raised to 2 raised to 8 minus 6 on both sides of the congruence. We check that 41 raised to 3 times the value we just applied is not congruent to 1 modulo 769, so we need to square again. The next step is now computing the order 2 raised to I of the bracket on the right side of the congruence. And so we need to check values, keeping in mind that I is smaller than h. We find that I equals 3. Thus, we apply 7 raised to 3 times 2 raised to 8 minus 6 raised to 2 raised to 6 minus 3 on both sides of the congruence. This time, we check that the product of the two brackets at the right side of the congruence are congruent to 1 modulo 769, so we reach the solution. Note that the solution can be expressed more clearly with the Tonelli-Shanks formula. The usual way of Tonelli-Shanks algorithm is to work with residues modulo 769 at each step, as seen with the numbers in gray, thus reaching the solution. 612 squared is congruent to 41 modulo 769. We could also apply the formula previously derived and reach the same solution, as seen in yellow. Yet, to make the formula work, you need to derive the order 2 raised to h and 2 raised to I, and you can't do that if not going through the algorithm. Beforehand, you cannot know how many multiplicative orders 2 raised to k sub m you'll need to compute. The only thing we can say beforehand is that once you compute the value of h, which is equal to 6, the sum of the reciprocals of the order lies in the range 1 over 64 to 63 over 64. So the formula doesn't really give an advantage over the algorithm. Nevertheless, it nicely shows how those k sub m values impact in the method. Well, let's now get back to the infinite descent method developed previously and check how it performs for the same case. Press pause if needed. Finally, it's interesting to compare the Tonelli-Shanks and infinite descent formulas when applied to this specific case, finding the modular square root congruent to 41 modulo 769. Despite their apparent differences in structure, both methods fundamentally rely on the same principles, utilizing the properties of quadratic residues and non-residues to achieve their results. Similarly, consider another example from section 2, finding the modular square root congruent to 17 modulo 353. Tonelli-Shanks algorithm relies on the multiplicative order of 2 raised to k modulo p, while the method developed in this presentation starts with a variation of Niven's congruence and uses infinite descent to find the solution. Despite the different approaches, the outcomes at each step are quite similar. Both methods yield the same base on the left-hand side of the congruence, differing solely in the exponents. That's because R sub I equals k minus k sub I minus 1. So we're going one step further from the multiplicative order of 2 raised to k, dealing with sum of squares, a raised to 2 raised to k minus 1 congruent to minus 1 modulo p. Both methods require roughly the same number of computations. The first one involves computing orders 2 raised to k sub I modulo p, while the second involves checking divisibility at each step of the factors of difference of squares, m raised to 2 raised to t plus 1 minus n raised to 2 raised to t. The infinite descent method is particularly appealing due to its inherent elegance and its role as a conceptual counterpart to Tonelli-Shanks algorithm. In this section, we analyze Tonelli-Shanks algorithm, offering a clearer display of its mathematical building blocks. This analysis allows us to derive a Tonelli-Shanks formula. While this formula does not provide an advantage over the usual algorithm, it offers insight into the role of the multiplicative order in finding the modular square root. We then compared Tonelli-Shanks algorithm to the infinite descent method. Despite the different approaches, we found that the outcomes at each step are quite similar, and both methods require roughly the same number of computations. However, it is important to note that the infinite descent method is applicable only for primes of the form 8k plus 1. By contrast, the Tonelli-Shanks algorithm is universally applicable to all primes. although it's particularly efficient for those of the form 4k+1. To end, the infinite descent method is equally effective computationally for finding a modular square root. Plus, it offers enhanced clarity and elegance in its intermediate steps. Moreover, it serves as a valuable pedagogical introduction to the more general Tonelli-Shanks algorithm. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.